Module 6, Part 1, Hypothesis Testing. Introduction. The logic of hypothesis testing. When interpreting an experimental finding, a natural question arises as to whether the finding could have occurred by chance. Hypothesis testing is a statistical procedure for testing whether chance is a plausible explanation of an experimental finding. Following is an example based on James Bond to help explain the concept of hypothesis testing. Bond insisted that martinis should be shaken rather than stirred. Let's consider a hypothetical experiment to determine whether Mr. Bond can tell the difference between a shaken and a stirred martini. Suppose we gave Mr. Bond a series of 16 taste tests. In each test, we flipped a fair coin to determine whether to shake or stir the martini. Then we presented the martini to Mr. Bond and asked him to decide whether it was shaken or stirred. Let's say Mr. Bond was correct 13 of the 16 taste tests. Does this prove that Mr. Bond has at least some ability to tell whether the martini was shaken or stirred? This result does not prove that he does. It could be he was just lucky and guessed right 13 out of 16 times. But how plausible is the explanation that he was just lucky? To assess its plausibility, we determine the probability that someone who was just guessing would be correct 13 out of 16 times or more to be 0.0106. We aren't going to worry in this class about how those probabilities are calculated. This is a pretty low probability. It means that a person could be expected to get 13 out of 16 right just by guessing only one time in every 100 trials of the experiment. Therefore, someone would have to be very lucky to be correct 13 or more times out of 16 if they were just guessing. So, either Mr. Bond was very lucky, or he can tell whether the drink was shaken or stirred. The hypothesis that he was guessing is not proven false, but considerable doubt is cast on it. Therefore, there is strong evidence that Mr. Bond can tell whether a martini was shaken or stirred. Another example, a case study, Physicians' Reactions, sought to determine whether physicians spend less time with obese patients. Physicians were sampled randomly and each was shown a chart of a patient complaining of a migraine headache. They were then asked to estimate how long they would spend with the patient. The charts were identical except that for half the charts the patient was obese and for the other half the patient was of normal weight. The chart a particular physician viewed was determined randomly. 33 physicians viewed charts of average weight patients and 38 physicians viewed charts of obese patients. The mean time physicians reported that they would spend with obese patients was 24.7 minutes as compared to a mean of 31.4 minutes for average weight patients. How might this difference between means have occurred? One possibility is that physicians were influenced by the weight of the patients. On the other hand, perhaps by chance, the physicians who viewed charts of the obese patients tend to see patients for less time than other physicians. Random assignment of charts does not ensure that the groups will be equal in all respects other than the chart they viewed. In fact, it is certain the groups differed in many ways just by chance. The two groups could not have exactly the same mean age, if measured precisely enough, such as in days. Perhaps a physician's age affects how long physicians see patients. There are innumerable differences between the groups that could affect how long they view patients. Therefore, it is possible that these chance differences are responsible for the difference in times. To assess the plausibility of the hypothesis that the differences are due to chance, we compute the probability of getting a difference as large or larger than the observed difference, which would be 6.7 minutes, if the difference were, in fact, due solely to chance. Using methods that are not covered in this course, this probability can be computed to be 0.0057. Since this is such a low probability, we have confidence that the difference in times is due to the patient's weight and is not due to chance. It is very important to understand precisely what the probability values mean. In the James Bond example, the computed probability of 0.0106 is the probability he would be correct on 13 or more taste tests out of 16 if he were just guessing. It is easy to mistake this probability of 0.0106 as the probability he cannot tell the difference. This is not at all what it means. The probability of 0.0106 is the probability of a certain outcome, 13 or more correct out of 16, assuming a certain state of the world that James Bond was only guessing. It is not the probability that a state of the world is true. It's not the probability that on any given test he's going to be wrong. Although this might seem like a distinction without a difference, consider the following example. An animal trainer claims that a trained bird can determine whether or not numbers are evenly divisible by 7. In an experiment assessing this claim, the bird is given a series of 16 test trials. On each trial, a number is displayed on a screen, and the bird pecks at one of two keys to indicate its choice. The numbers are chosen in such a way that the probability of any number being evenly divisible by 7 is 0.50. The bird is correct on 9 out of 16 choices. 9/16, or as a decimal, 0.56, or 56%. The probability of being correct 9 or more times out of 16, if one is only guessing, is 0.40. Again, we're not worried in this class with how to compute this value. Since a bird who is only guessing would do this well 40% of the time, these data do not provide strong evidence that the bird can tell the difference between the two types of numbers. As a scientist, you would be very skeptical that the bird had this ability. Would you conclude that there is a 0.40 probability that the bird can tell the difference? Certainly not. He has a 40% chance of getting, on average, about 7 out of 16 correct just by guessing. It does not mean that he has a 40% chance of being correct on each particular number. To reiterate, the probability value is the probability of an outcome, 9 out of 16 or better, and not the probability of a particular state of the world, that the bird can tell whether a number is actually divisible by 7. In statistics, it is conventional to refer to possible states of the world as hypotheses, since they are hypothesized states of the world. Using this terminology, the probability value is the probability of an outcome given the hypothesis. It is not the probability of the hypothesis given the outcome. This is not to say that we ignore the probability of the hypothesis. If the probability of the outcome given the hypothesis is sufficiently low, we have evidence that the hypothesis is false. However, we do not compute the probability that the hypothesis is false. In the James Bond example, the hypothesis is that he cannot tell the difference between shaken and stirred martinis. The probability value is low, thus providing evidence that he can tell the difference. However, we have not computed the probability that he can tell the difference on any given taste. The heart of hypothesis testing. A friend of yours wants to play a simple game in which a coin is flipped. If the coin comes up heads, you win. If it comes up tails, your friend wins. Suppose that the outcome of 5 plays of this game is tails, 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 tails. Is your friend cheating you? On each flip of a coin, there is a 1 out of 2, or a 1/2, or as a decimal, a 0.50, or as a percent, it would be a 50% chance of getting a tail. So the likelihood of getting 5 tails in a row would be 0.03125. This means if we flipped a fair coin 5 times and repeated this experiment of 5 flips 100 times, we would expect about 3 of the 100 trials to result in all tails. 0.03 is equal to 3 out of 100. It is possible to get 5 tails in 5 flips of a fair coin, but it isn't very likely. You can come to one of two conclusions here. Your friend is not cheating you and just happens to be very lucky. Your friend is not using a fair coin and is cheating you. Are you willing to accuse your friend of cheating, or did you just happen to experience an unusual result from a fair coin? This is the heart of hypothesis testing. We make an assumption about reality. We then look at or gather sample evidence to determine whether it contradicts our assumption. The objectives in this lesson are to determine the null and alternative hypotheses, to understand statistical significance, to explain type 1 and type 2 errors, and to state conclusions to hypothesis tests. First, we'll focus on determining the null and alternative hypotheses, and the notation for the null is an H sub 0. The alternative hypothesis notation can either be an H sub 1 or some authors use an H sub A. An hypothesis is a statement regarding a characteristic of one or more populations. In this module, we look at hypotheses regarding a single population parameter. The hypothesis that an apparent effect is due to chance is called the null hypothesis. In the physician's reaction example, the null hypothesis is that in the population of physicians, the mean time expected to be spent with obese patients is equal to the mean time expected to be spent with average weight patients. In other words, the null hypothesis is the physicians don't spend different amounts of time based on weight. And the notation could be that the HO, or the null hypothesis, is that the mean time spent with obese patients is equal to the mean time spent with average weight patients, or we could express that same sentiment by saying that the difference in the two means would be equal to 0, because if the two means are equal, if we subtract them, we're going to get 0. Although the null hypothesis is usually that the value of a parameter is 0, there are occasions in which the null hypothesis is a value other than 0. For example, if one were testing whether a subject differed from chance in their ability to determine whether a flipped coin would come up heads or tails, the null hypothesis would be that that probability is equal to 0.5. Keep in mind that the null hypothesis is typically the opposite of the researcher's hypothesis. In the physician's reaction study, the researchers hypothesized that physicians would expect to spend less time with obese patients. The null hypothesis that the two types of patients are treated identically is put forward with the hope that it can be discredited and therefore rejected. If the null hypothesis were true, a difference as large or larger than the sample difference of 6.7 minutes would be very unlikely to occur just by chance. Therefore, the researchers rejected the null hypothesis of no difference and concluded that in the population, physicians intend to spend less time with obese patients. If the null hypothesis is rejected, then the alternative to the null hypothesis, which is called the alternative hypothesis, is accepted. The alternative hypothesis is simply the reverse of the null hypothesis, that the two means were equal. The alternative hypothesis is simply the reverse of the null hypothesis. If the null hypothesis that the two means are equal is rejected, then there are two alternatives. Either the mean time spent with obese people is less than the mean time spent with average people, or the mean time spent with obese people is greater than the mean time spent with average weight people. Naturally, the direction of the sample means determines which alternative is adopted. Question. Tommy claims that he blindly guessed in a 20-question true-false test, but then he got an 80%. Using the binomial calculator, and we're not going to worry about calculating probabilities in this course, all you need to know is the probability of getting 16 or more correct out of 20 when the probability on any one question is 0.5 is 0.0059. This probability of 0.0059 is the probability that, stop the video and make your choice before you continue on to the next slide. If Tommy were guessing blindly, the probability that he would have gotten 16 out of 20 questions right is 0.0059. This is not the probability that he was guessing blindly. Remember, the probability value is the probability of an outcome given the hypothesis. It is not the probability of the hypothesis given the outcome. So this is not the probability that he would get an 80% if he took the test again. It is also not the probability that he was guessing blindly. The assumption is that he was guessing, and we want to know what is the likelihood that he would get at 80% given that he's just guessing. Another question. A researcher believes that second graders will score higher than first graders on a particular test. Which of the following is the null hypothesis? Stop the video and make your selection before looking at the answer on the next slide. The null hypothesis says that any apparent effect is due to chance. So in this case, the null hypothesis would be that the two population means for the first and second graders are equal. The null hypothesis is usually not the researcher's hypothesis. It's not what the researcher is setting out to gather evidence for. Also, the null hypothesis will be the one with the equal in it. Another question. The researchers hypothesized that there would be a correlation between how much people studied and their GPAs. Recall correlation values R range between -1 and 1. The null hypothesis is that the population correlation is equal to... Stop the video and answer the question before looking at the answer on the next slide. The correct answer is 0. The null hypothesis says that any apparent effect is due to chance, so in this case the null hypothesis would be that the population correlation was 0. Recall r equals 0 represents no correlation between the variables being studied. Now take the Module 6 Part 1 assessment of learning. The password is null.